Lesson 8.5, Intersections of Lines and Planes. So we're familiar with working in two-dimensional space where the whole thing is a plane, and all we can really talk about are points and lines. And we know that lines can interact in one of three ways. They can either be parallel to one another, in which case they never intersect, or they can be intersecting, have different slopes, whatever those slopes may be, or the two lines can be coincident lines, in which case they are the same line, and they have an infinite number of solutions, an infinite number of intersections, I guess you could say, but an infinite number of solutions. They're right on top of each other. In three-dimensional space, we talked about the relationship between lines already. We said there were four different ways that they could interact. They could be parallel to one another, they could intersect, or they could be coincident, and then there was a fourth option of skew, in which case they are not parallel, yet they still don't intersect. So that's the relationship of lines in 3-space. Well, now we're still in 3-space in lesson 8.5, but we're talking about the relationship between a plane and a line. And there are now 3 ways that they can interact with each other. Go ahead and take a second and see if you can figure out the 3 ways that they could possibly interact with each other. Alright, so we remember that planes go infinitely in every direction. Lines go infinitely in 2 directions. So there is one possibility here. The one possibility is that somewhere along this plane, somewhere on this plane, our line, L1, crosses through the plane. It hits it at a point and crosses through it. Okay, that's one possible relationship, is that it intersects at exactly one point, one solution. Okay, another option is that the line actually lays on the plane. So if you had L1 here, and here L1 lies on the plane, in which case every single point on the line intersects the plane. So there are an infinite number of solutions. And the last option that we're going to draw out is this option right there. We've got L1. It is parallel to the plane, but it is above the plane. It's up off the plane, as though it went kind of up on the z-axis. So this is no solutions, no intersection. Okay, they do not intersect. Three options: one point of intersection, infinite number of points of intersection, no points of intersection. One solution, infinite number of solutions, no solutions. Here we go. So in example 1, we're going to experience all 3 of these possible interactions or non-interactions between a line and a plane. And so we're given in A, there's going to be A, B, C. I'm just going to write A for now. We're given the equation of a plane. Now you see the pi symbol here. That does not mean 3.14 yada 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 yada. Okay, it's the use of the pi symbol in symbolizing or representing just the word plane. So this is plane number 1. Okay, plane number 1 is 9x plus 13y minus 2z equals 29. And the line we're given in its parametric parts here, we're given x equals 5 plus 2t, y equals negative 5 minus 5t, and z equals 2 plus 3t. So in case we're forgetting, this could be the line, this is the line x, y, z equals our position vector 5, negative 5, 2 plus some scalar multiple of 2, negative 5, 3. Okay, here it is in vector form, here it is in its parametric equation. And so what we're really looking for here is we want this x to be that, and this y to be that y, and this z to be that z. They all need to match up, which means that there needs to be a single value of t that makes this x fit there, and this y fit there, and this z fit there, all at the same time. okay? So we're looking for a value of t that makes this work, basically, okay? So what I'm going to do is simply take our parametric pieces, our parametric equation, and we're going to put them in here. We're going to sub them into our equation for a plane, because if this is going to be true, if there's going to be a spot where these things interact, then a solution x, y, z for the plane is going to also fit x, y, z for our line. They're going to be the same thing at the same time. So here we go. Inside our equation for a plane, I'm going to take that and go 9, and for x, I'm going to put in 5 plus 2t. Then I'm going to add 13y, but for y, I'm going to put in -5 minus 5t, and -2z, but for z, we're going to put in 2 plus 3t, rounded brackets, equals 29. So now I'm going to expand and solve for t, and we're going to see how many values of t end up being solutions for this problem. So 9 times 5 is 45 plus 18t minus 65 minus 65t minus 4 minus 6t equals 29. Group my t's on the left, move everything else to the right. I've got 18t minus 65t minus 6 more t. That's going to be negative 53t. And for my constants, I have 45 minus 65 minus 4. And then I'm going to be adding that to both sides. It's going to leave me with 53 on the left. So we have negative 53t equals 53. Divide both sides by negative 53. We get t equals -1. What did we do there? We sub parametric equations into pi1, plane 1. Then you expand and solve for t. All right, what do we find out here? There is a single value of t. T equals -1. Therefore, there is a value of t and only one value of t that makes these guys all sub into there nice and neatly. Okay, that means these guys this plane and line are going to intersect at a single point. Since a single value of t was found, plane 1 and L1 intersect at a single point. Now to find out what that point is, all we need to do is sub our value for t back into our parametric equation. So we have for x, the x coordinate is going to be 5 plus 2 times -1. The y coordinate is going to be -5 minus 5t, 5 times -1. And the z coordinate is going to be 2 plus 3 times -1. So x is 5 minus 2, which is 3. Y is -5 plus 5, which is 0. And z is 2 minus 3, which is -1. Therefore, pi1, plane 1, and I'll try to stop saying pi1. Plane 1 and line 1 intersect at 3, 0, -1. Rounded brackets because it's a point, not a vector. In part B, we are given plane 2 is x plus 3y minus 4z equals 10. And line 2 has the parametric equation x equals 4 plus 6t, y equals negative 7 plus 2t, z equals 1 plus 3t. So again, we're going to follow the same process. We're going to sub in x, 4 plus 6t, plus 3 times y, negative 7 plus 2t, minus 4 times z, which is 1 plus 3t. Now we're able to do that. We're testing to see if there is a value of t that satisfies both equations, that would allow x, y, z, a certain combination of x, y, z to satisfy both sets of equations. So continue to expand and simplify. We've got negative 21 plus 6t minus 4 minus 12t equals 10. Keep my t's on the left. We've got 6 plus 6 is 12, minus 12 is 0t equals, and now we've got 4 minus 21 minus 4, so that's going to be negative 21. I'm going to add 21 to both sides. Gives me 0t equals 31. Well, how many values of t will satisfy this equation? Okay, or you could try to divide both sides by 0 and you'd get a non-answer over here, an undefined value. So this tells me that there is not a single value of t that can satisfy this equation. Therefore, the line and the plane do not intersect since no value of t can satisfy this equation. Plane 2 and L2 do not intersect. If it does not intersect, it must be parallel to the plane but distinct from the plane. They do not intersect. L2 is parallel, that's not spelled right, parallel and distinct. So it's not lying on it, even though it's parallel to it. It's parallel and distinct to plane 2. All right, I'm going to fit C on here as well. C, we're given the plane 3, which is 4x minus y plus 11z equals negative 1. And this time we're given our line 3 in vector form. It's x, y, z is equal to the position vector negative 2, 4, 1 plus some scalar multiple of our direction vector 3, 1, negative 1. And we're able to do the exact same thing here. We're just going to kind of draw out our parametric equations for the line from here. But we know that x equals negative 2 plus 3t, y equals 4 plus t, z equals 1 minus t. Okay, and we're going to sub those in to our equation for our plane. So 4 times negative 2 plus 3t minus y, which is 4 plus t. Notice I have to put those in brackets. Please don't forget to put y in brackets because this negative symbol is going to distribute and apply to both pieces, okay? And then we have 11 times z, which is 1 minus t equals negative 1. Expand and simplify. Negative 8 plus 12t minus 4 minus t plus 11 minus 11t equals negative 1. our t's, 12t minus 1t minus 11 more, that gives me 0t. And on the right hand side, well, we've got negative 8 minus 4, that's negative 12 plus 11, that's going to be negative 1. Add that to both sides, it's going to get me 0 on the right side. So now we have a different situation. So we have 0t just like we had before, but in the last one we had to make 0t equal 31. Well, that's impossible because anything times 0 is what? Is 0. That means down here, any value of t will satisfy this equation. Does not matter what I make t, it's going to get multiplied by 0, it's going to equal 0. Okay? This equation is true for all values of t. So now, since any value of t here will make this true, that means that any point along this line is a solution. So this line lies completely on the plane. Therefore, any point along the line is a solution. Therefore, let's call it by its name, L3 lies on plane 3. Okay, so there you have a quick example of each. In example 1a, they were intersecting at one point. Example 1b, they did not intersect at all because there were no values of t that could satisfy the equation. And in example 1c, the line was on the plane, an infinite number of solutions because any value of t can satisfy that equation. All right, just like in previous lessons, we learned how to do something, and then I said, there's another way to do it. So same thing is going to happen here. You can solve the equations like we did in example 1, but if a plane, there's my plane, and a line are not perpendicular to one another, and the line goes on forever and the plane goes on forever, then you can be certain that there is a spot where they are going to intersect, okay? So all we need to do is make sure that they're not parallel to one another. Well, how do we do that? All we need to do then is have the direction vector of the line, because you could talk about this portion of the line or this portion of the line or this portion of the line or this portion of the line. It makes no difference. A line goes on forever. So all we need is the direction vector, and that's going to determine our where the line can go. And for the plane, what we need is the normal vector of the plane. So remember, the normal vector is any vector that comes off of this plane at a right angle, okay? So the normal vector is perpendicular to the plane. If then the normal vector is also perpendicular to the line, then you know the plane and the line are parallel and they do not intersect. If the normal vector is perpendicular to the plane, which it is by definition, but it is not perpendicular to the line, then you know that somewhere, some way, this line is going to hit that plane. It's going to intersect with that plane. Okay, so what we're checking for, we're going to be given a plane. We're going to find its normal vector, which is really easy if we have the plane in standard form. And we're going to be given a line, and we're going to take the direction vector. And what are we going to use? What tool are we going to use? Okay, we're going to take the dot product. And if the dot product is 0, okay, between the line, the vector, and the normal, then we know they are perpendicular. And in this case, there's going to be no solutions, no intersection between the line and the plane because they're parallel to one another. But if it is anything other than 0, we know that the angle between them will not be 90 degrees, which means the plane and the line will not be parallel, and they will intersect. So here we go. In example 2, it says without solving, determine if the line intersects the plane. So in example 2a, there's going to be a and b. We're given the line 1 is the vector 2, -5, 3 with direction 3, 2, 1. And we're given the plane 3x minus y plus z equals -6. So again, we're looking for the, let's just do it underneath, direction vector of L1. It's the direction vector of the line. That is direction vector M, 3, 2, 1. And we are looking for the normal vector of the plane. Normal vector of plane 1, which is the vector n equals, and remember we just take the coefficient of each of the coordinates. So we've got 3, -1, +1. And now what we need to do is see if these are perpendicular to one another. So we're going to consider the dot product m dot n to see if they are perpendicular or not. So if they are perpendicular, that means that the line and the plane are parallel. If they are not perpendicular, that means the line and the plane will intersect. So here we go. We've got m dot n. That's going to equal 3 times 3, 3 times 3, plus 2 times -1, plus 1 times 1. 9 minus 2 plus 1 equals 8. Okay. Since m dot n does not equal 0, they are, shouldn't say they are, m and n are not perpendicular. Therefore, line 1 will intersect plane 1. Okay, we do not need to say where they intersect. We just need to know, since they're not parallel, they must intersect. In B, we have the line 2 is the vector r, which equals 1, 0, 1, plus some scalar multiple of -2, 1, -4. And we have plane 2, which is 4x minus 2z equals 11. And we're going to follow the same process. We're going to get the direction vector of line M, direction vector of line 2, direction vector of L2, which is M equals -2, 1, -4. So we don't actually care in this calculation what we're working with. It doesn't matter to us the position vector of line 2. Because we know it's going to go forever and ever in this direction. So as long as this direction isn't parallel to the plane, then they're going to intersect. Here we go. We need the normal to plane 2. It's going to be our normal vector, which is the x-coordinate coefficient, which is 4. The y-coordinate is 0. And the z-coordinate is -2. Now we're going to take m dot n, which is, and I'm not going to do that, negative 2 times 4 plus 1 times 0 plus negative 4 times negative 2. That's negative 8 plus 0 plus 8. That's 0. So because because the dot product is 0, that tells us the vector m is perpendicular to the vector n. And because they are perpendicular, that means that the line is parallel to the plane. Therefore, L2 is parallel to plane 2. So now we have two options. They're either coincident, that is, the line lies on the plane, or they are distinct, in which case the line is parallel to the plane but not on the plane. So we can still test that. Now we can take our position vector from the line and we can test simply to see if that point is on this plane, then the whole line is on the plane. Okay? Does that make sense? We already know that it's parallel to the plane, so it's either on the plane or it's above the plane or below the plane or beside the plane, something like that, depending on what this plane looks like and what the line looks like. But we can test to see if this point is on the plane. If this point is on the plane, then the whole line is on the plane, because this line starts at this point and goes both directions in this direction. Okay? So here we go. I'm going to simply test to see whether 1, 0, 1 is on the plane. So test to see if 1, 0, 1 is on the plane to determine if L2 and plane 2 are coincident or distinct. So we're going to go left side, right side. Left side of our plane is 4x minus 2z. Right side is 11. Sub in what I know. X is 1. Z is 1. 4 minus 2 is 2. That does not equal right side. What does that tell us? They are parallel and distinct. L2 and plane 2 are parallel and distinct. So again, using the dot product of the direction vector from the line as well as the normal vector from the plane. If that comes out as 0, then the line and the plane are parallel. That didn't in this case tell us if they were distinct or coincident, so we had to do a little test of the point that we know from the line and see if it is actually on the plane. If this comes out as non-zero, then that means they are not perpendicular. The normal and the direction vector are not perpendicular, therefore the line will intersect the plane at some point. Okay, if we know that a point is not on a plane, like we did in example 2b, we found out that we had a point that was not on a plane, and that told us that the line and the plane were distinct. The next question would be then, well, how far away is that point from the plane? So that's what we're going to be figuring out in example 3. In example 3a, we're given a point. Well, let's give the plane first. Okay, so we're given the plane. We're going to use this plane for both examples, but the plane is 4x plus 2y plus z minus 16 equals 0. And in A, we're going to determine whether or not the point P, which is 10, 3, negative 8, what is the distance from that point to the plane? So the first thing we want to do is check to see if the distance is 0. We can check to see if the point P is on the plane. So check to see if P is on the plane. We do that really simply using left side, right side. So we've got the left side of our plane is for x, and I'm just going to sub in my values right away, plus 2y plus z, which is -8, minus 16, and the right-hand side we have 0. So here I have 4 times 10 is 40, plus 6, minus 8, minus 16. This is not going to be 0, okay? So I'm just going to say is not equal to right side, which means it's not on the plane. Okay, so now it's some distance from the plane. Okay, maybe it's here. We've got the point, 10, 3, -8. I don't know how this point and this plane interact, but this is a generic drawing that will help us understand it a little bit. Now we can be certain that there is a vector that will get us from the plane to point P. Now, what type of vector is that going to be? Well, it's going to be parallel to the plane. Sorry, perpendicular to the plane. This red stick is going to be the normal vector to the plane, and we know how to get the normal vector. So we know the direction this vector is going, but we really still don't know the distance. In order to know the distance, I would like to have this point. Okay? Well, I can't get that point. I don't know where it is because I don't know how far down this plane is from this particular point. So what I can do is actually use a similar strategy to the one we used a little while ago. And what I can do is I can pick any arbitrary point that is on the plane. Okay, so I'm going to name our points. We're going to have point Q over here. And what it's going to be is it's going to be any point on the plane. Well, how do I do that? I'm going to write generate point Q by selecting, well, let's call it generate point Q on the plane by choosing values for x and y, then solving for z. So here's what we would do then. We can pick any two values for x and y and solve for z in a way that it will still satisfy this equation. That means that it's going to be, that point is going to be on the plane, okay? So we're going to start with x equals 4, y equals 0, and then we're going to solve for z. And what happens if we put 4 times 4 is 16, y is 0. That's going to give us 16 plus z minus 16 equals 0. 16 minus 16 is 0. It's going to give us z equals 0, okay? I know I just did it orally. You might have to do it on a piece of paper, but I just wanted to get past that point. So this tells us that 4, 0, 0 is on the plane. Okay, so we have Q400, and we're going to name this guy O. And what we've really done here is we've created a bit of a triangle, haven't we? We have the vector PQ, we have the vector QO, and we have the vector OP. And since this is normal, the red line, the red vector OP is normal to the plane, and OQ is on the plane because O is on the plane and Q is on the plane, then we know what we've done is actually created a right angle triangle here. And if we go back to what we know about projections, then the projection of PQ onto N, onto OP, the projection of QP onto the normal vector, so onto the vector in the direction of N, will be the length, will have the magnitude OP. Okay, so that is what we're looking for. Okay, let's make a note of that. The projection of QP onto N gives or should say has the same length, has the same length as OP. Make sure these are vectors, which is the distance from the point to the plane. All right, so let's figure this out. We've got PQ is equal to the position vector for Q, which is 4, 0, 0, minus the position vector for P, which is 10, 3, negative 8. And I'm realizing I should have not named this point O. I should have left O to represent the origin, in which case the position vector O, to Q could be the vector OQ. OQ would be 4, 0, 0, and OP would be 10, 3, negative 8. I didn't do that. I named that point when you don't actually need to name that point. But we'll just carry this through. It's the same thing. I'm looking for the vector PQ, and I can get it by taking the difference from P to Q. So Q, point Q, take away point P. Here we go. 4 take away 10 is negative 6. 0 take away 3 is negative 3. 0 take away negative 8 is positive 8. So there is my vector PQ. And now, in order to find the distance here, I'm finding the projection of QP onto N. That means that the distance, which is the projection of PQ onto N, is done using my projection formula. So I take in the numerator the magnitude of the dot product of N and PQ. And in the denominator, we have the magnitude of the vector N. So in the numerator, taking the dot product of N and PQ. So N, I'll just rewrite it here since I think it's gone. N comes from the equation for the plane. So it's just 4, 2, 1. 4, 2, 1. Okay, there it is. Now I'm taking the dot product between that and PQ. So I've got negative 6 times 4, which is negative 24, plus negative 3 times 2, which is negative 6, plus 8 times 1, which is 8. And in the denominator here, I have the magnitude of vector n, which is the square root of a squared plus b squared plus c squared. So I've got 4 squared plus 2 squared plus 1 squared. Next step, negative 24 plus 2 is going to be negative 22. And here I'm going to have 16 plus 4 plus 1, that's 21, radical 21 in the denominator. And if I estimate that value in my calculator, I get 4.8. Okay, therefore, the distance between point P and the plane is approximately 4.8 units. All right, not so difficult there, as long as we remember the relationship between our projection and the distance between. You create the normal vector from your equation for the plane, and you just have to remember to choose any point on the plane, and you do that by choosing two of the coordinates and then solving to find the third coordinate. Okay, we could have chosen 1 and 0 and then seen what z was, and this would work out the same way. You get the exact same answer. Okay. In example 3b, we have the same plane that we had in the first example. This time we have a different point. And again, your first step is to check to see whether or not this point is on the plane or not. And when you do that, when you sub in left side, right side, you'll sub in 2 for x, 2 for y, 4 for z. You'll find out that this section equals 16, take away 16 equals 0. So left side does equal right side, which tells you that this point is on the line, which tells you that the distance is 0. And I'm not going to do the work because we just did something like that. Since point B is on the line, sorry, on the plane, the distance is 0 units. And that wraps up lesson 8.5, intersections of lines and planes. Your practice problems begin on page 479, and you're responsible for knowing how to do 1 through 16. Thanks for watching.